learned how to determine rate laws experimentally, and we've learned that we need to determine rate laws experimentally because the stoichiometry doesn't always reflect the actual rate law. But why is that? I mean, if I took a reaction like the combustion of hydrogen to create water, the balanced reaction looks like that. I would expect, just from looking at the stoichiometry, that the rate law would look something like this, with a squared hydrogen. Because after all, it takes two hydrogens to react with that oxygen to produce this water. This reaction happens extremely quickly regardless. I mean, we've blown up hydrogen in the lab before, but the rate might not reflect that. Why is that? Well, the reality is that even if this is what our completed reaction looks like, there could be intermediate steps that we're not aware of happening inside this arrow. Let's look at an example of that. A common reaction could be dinitrogen pentoxide, N2O5, reacting with nitrogen trioxide to form 3 nitrogen dioxides and 1 molecule of oxygen gas. The rate of this reaction, we would expect, just looking at this, that we would have a second order reaction, depending on the concentration of N2O5 and the concentration of NO3. But if we look at the actual rate law, we have a second order for N2O5. Now, why is that? Well, the reality is this reaction doesn't just proceed straight this way. It actually has a bunch of steps in between. 3, to be precise. And during those steps, we don't see what's going on. All we see is that we put these reactants in and got these products out. We actually have to go through and theorize what those steps could be and then test during the reaction to see if we're right. We'll look at more multi-steps later, but for now I just want to use this as an example. We start with N2O5. Without involving the nitrogen trioxide, the N2O5 will dissociate into NO2 and NO3. These two, not this NO3, but this NO3, will react again with each other to produce nitrogen monoxide, nitrogen dioxide, and oxygen gas. Just from this part of the reaction, we get one of our 3 nitrogen dioxides and our oxygen gas. So this is the first 2 products that we get, but we still have this nitrogen monoxide that we don't see at the end, and this initial product of nitrogen trioxide that we haven't used yet. So in our final step, this NO reacts with NO3 to produce our last 2 NO2s. So we have a 3-step reaction happening here. And each of these steps is what we call an elementary reaction. An elementary reaction is a reaction that is one and only one step. When we have an elementary reaction, the stoichiometry of that reaction will accurately reflect the rate law. So the rate law for just this single step should be a first order N2O5. The rate law for this single step should be first order NO2 and first order NO3, which combined would make another first order N2O5. So from these 2 steps, we see that we actually doubly depend on the N2O5. That's how this is able to make sense. Let's break out our ball and stick models and look at 3 more examples in order to better understand this concept. First up, we have the reaction of chloromethane. That's a methane group with a chlorine attached in place of one of the hydrogens, reacting with a hydroxide anion. This reaction is an elementary reaction. This whole thing happens in one step. It's a very commonly known mechanism in organic chemistry. There's a lot of reactions that proceed this same way. What happens is if I have this chloromethane, I've got a carbon with 3 hydrogens connected to a chlorine. This hydroxide will come along and attack from the backside. And when that happens, this carbon would much rather form a bond with this oxygen than this chlorine. And all at once, it has this kind of intermediate step, kind of this pseudo step, where it's half attached to the chlorine and half attached to the OH, while still being attached to the hydrogens. And then this snaps, and we end up with a methanol. So this mechanism really operates based completely on the concentrations of both of these materials. If I have a chloromethane sitting here, it can just be floating around, and if it doesn't encounter a hydroxide, it's not going to react. Nothing's going to happen. If I have a sample of this in a solution of water, well, these two could interact and nothing's going to happen. The reaction doesn't depend on water, it depends on hydroxide. So the reaction will proceed according to how many hydroxide ions are in the water. Remember, water can dissociate naturally into hydroxide and hydrogen ions. So this hydroxide could then interact with this chloromethane and form that methanol. In one step, it would replace this chlorine. This is why understanding this mechanism is important, because if it had to wait for this chlorine to move in order to attach, like this in the ball and stick model, that would be two steps. We'd have a different rate law. But because this is our rate law, we're able to figure out that actually what's happening is this hydroxide attacks from the backside, and the chlorine is let go. When we understand that, we can see that this rate law perfectly reflects our stoichiometry because it's all happening at one time. So how could we increase the rate of this reaction? Well, it'd be very easy. We would just increase the concentration of our CH3Cl, or we could just increase the concentration of hydroxides. So if we were in a solution of water, something we could add is sodium hydroxide. So that's why we would see a reaction going forward with CH3Cl plus NaOH would actually increase the rate of this reaction because we'd add more hydroxides to our concentration. By increasing that concentration, we increase our rate. So we can see that because of the mechanism of this reaction, this elementary reaction, we have a rate law that reflects our stoichiometry. Let's look at another one. In this reaction, we have cyclobutane, which is C4H8, dissociating into two ethenes. This reaction is another example of an elementary reaction. This happens all at once, all together in one step. So our rate law reflects our stoichiometry. So we have one C4H8 reacting, and our rate law is first order with respect to C4H8. So that makes sense. If we look at the mechanism behind this, we can really understand why this is first order, why this is an elementary reaction. Because if I have a sample of cyclobutane, we can see that this is a pretty, even just the ball and stick model, this is a pretty unstable molecule. In fact, I have to use these springs to put it together. It won't line up with the solid bonds. So this thing, even if I try to line up two of the springs, it causes the others to bow out. This molecule on its own is known to be a very unstable molecule. It doesn't like being in this configuration. And so what will naturally happen is just at any point in time, it'll break apart. But we're never going to have just one cyclobutane. This cyclobutane is going to be interacting with all the other cyclobutanes around it. It's going to be colliding with colossal speeds and forces. So just being inherently unstable, paired with all of these collisions, allows it to break apart quite easily. Now we've got a bond that wants to find a home. Now this could reform here, but what's more likely to happen is, since this is already unstable and this is unstable, these two are probably both going to break apart. And when they break apart, this bond's looking for a home, and it finds one in the carbon next door, the carbon that it's already got a bond with. And same thing here. This will find a bond with the carbon that it's already bonded with. And so we have these two this pair of ethenes coming out of this reaction very naturally and in one step. By understanding the mechanism, and by understanding this concept of elementary reactions, we can see why a rate law will sometimes reflect our stoichiometry. Let's look at another example where our stoichiometry does not reflect our rate law at all. I have here an example of the Haber process. The Haber process is extremely well known. It's a very common chemical process. It takes nitrogen gas, reacting it with hydrogen gas to produce ammonia. Ammonia is extremely important for fertilizers and explosives, but fertilizers more importantly, because if not for this process, if not for finding a way to increase the speed and the amount of ammonia that we get out of this process, we wouldn't be able to produce enough agriculture to support the number of people on the planet. So we really owe the ability to have 7 billion people on this planet to this chemical process. But the rate for this process doesn't depend on the concentration of any of the reactants. It is fully dependent on just the rate constant. That doesn't reflect the stoichiometry at all. You would expect, just from looking at this, that we would have something more like this. But that's simply not the case. The Haber process will proceed regardless of how many of these I have. It'll proceed at the same rate, no matter what my concentration is. There are other factors I can use to increase the rate of it, particularly pressure and heat, but my concentrations don't really matter that much. So, why is that? The reason is that the Haber process takes advantage of molecular nitrogen, which has this crazy stable triple bond. This does not want to bond with anything else. This is very happy being bonded with itself. It's perfectly fine staying like this forever. It bonds, it will react with 3 molecular hydrogens. But if we look at this, how likely is it that these 4 things would come together all at once and break apart and make this in one step? It's not likely at all. Having 4 things collide at the same time, even if we intentionally planned to have these 4 things collide in the air at the same time, like if we set up some catapults and launchers and tried to do that, we'd be so unlikely to succeed. So this is incredibly uncommon. It's just not going to happen. So how does this reaction proceed? Well, this is a very common reaction. It's so well studied that we actually know the different steps involved very well. And they actually proceed more like this. This isn't even all the steps. We have molecular nitrogen going from the gas phase into this pseudo phase in between before it can break apart. So the first thing that happens is this nitrogen breaks apart. It just separates from itself. And once that happens, it wants to get back together. It would much rather be molecular nitrogen than anything else in the world. But if it doesn't get back together right away, then what we have is our 3 hydrogens will break apart. So after the second step, this is what I have floating around. It's still incredibly unlikely that even 2 of these would collide with a nitrogen at once. And so instead what really happens is I get one of my nitrogens, colliding with one of my hydrogens. Boom, there we go. So now I've got nitrogen hydride. That's it. Once I've got that, now it's got to interact with another hydrogen. And now this collision could happen. And finally, this collision could happen. So it takes the course of 5 steps for this reaction to happen. And individually, these both have to get created. These both have to go through all of these steps in order to create this ammonia. So we can see what really has to happen here is that this nitrogen has to break apart and react with the hydrogen before it reforms. So because this is a really slow, unlikely thing to happen, it really doesn't matter how much nitrogen I have. It's still going to take a while. So my rate completely depends on the rate constant. It doesn't matter what my concentration of these is because all of these steps really eventually cancel each other out. So ultimately, the idea that we're trying to get across here is that each of these steps is an elementary reaction. Each single step is an elementary reaction. And the stoichiometry in these specific steps will have a rate law that reflects that stoichiometry. So ultimately, the point we're trying to drive home here is that a single step in a reaction, or a reaction that is a single step, is known as an elementary reaction. And in elementary reactions, the stoichiometry determines the rate law. This is important because if we understand what the elementary reaction is, we can more accurately manipulate these reactions to get the desired products.